Okay, so now that we finished learning about the concepts and Vieta's formula, let us consider some example problems. So first, I'm going to start with something very basic. So suppose we have some polynomial x3 plus 4x squared minus 6. Okay, so let's try to find S1, S2, and S3. So S1 is going to be equal to negative an minus. Okay, so I guess it's just going to be equal to 4 over 1, which is the coefficient of x3, and you multiply by negative 1, which is going to be equal to negative 4. And then S2 is going to be equal to negative 6 over 1, which is going to be equal to negative 6, because we're not going to multiply by negative 1 again. And then S3 is just going to be equal to negative 2 over 1, and then you're going to multiply the whole thing by negative 1, which is going to be equal to 2. So this is problem 1. Now let us move on to problem 2. So for problem 2, suppose we have a polynomial p of x, which is equal to x4 plus 6x3 plus ax2 minus 54x plus c. And suppose it has 4 real roots. R1, R2, R3, R4. And then also suppose that R1 plus R2 equals 0, and R4 minus R3 equals 4. And we want to find A and C. So how are we going to start this problem, right? Well, the easiest way we can start is by writing out Vieta's formulas. So we know that R1 plus R2 plus R3 plus R4, this is equal to S1, which is going to be equal to negative 6, because it's going to be negative 6 over negative 1. Or negative is going to be equal to 6 over 1 multiplied by negative 1. And then similarly, we have first using this S1, right? We can see that since R1 plus R2 over here is equal to 0, we know that R3 plus R4 is equal to negative 6, right? And at the same time, we have that R4 minus R3 is equal to 4. So this tells us that so that means we can add these two equations together, and then you can see that the R3s will cancel out, so this just becomes 2R4 is equal to negative 2. So R4 is equal to negative 1, and then R4 is equal to negative 1, and then R3 is going to be equal to 4 minus, is going to be negative R4, is going to be R4 minus 4, which is going to be equal to negative 5. So now we know what R3 and R4 are. And also we have, since we have that R1 plus R2 equals 0, right? And this means that R2 is equal to negative R1. Now what we can do is we can put this whole thing into S3. So what is S3? S3 is going to be equal to negative 54 over 1. And we're going to multiply this whole thing by negative 1 because it's S3 and 3 is odd. So that means S3 is going to be equal to R1, R2, R3 plus R1, R2, R4 plus R1, R3, R4 plus R2, R3, R4. These are all possible triplet products. And this is going to be equal to 54. Now, we can also substitute in the values of R4 and R3, right? So this gives us, this is going to be equal to R1 times negative R1, right? Because we have it from here, times R3, which is going to be equal to negative 5, plus, I'm just going to, okay, plus R1, negative R1, negative 1, plus R1, negative 5, negative 4, negative 1, plus negative R1, negative 5, negative 1. And if we multiply everything together, this gives us 5R1 squared plus R1 squared plus 5R1 minus 5R1 equals 54. And we can see that this cancels out, leaving us with 6R1 squared is equal to 54. And so R1 squared is equal to 9. So that means R1 is equal to 3 or negative 3. And since R2 is negative R1, right? R2 is just going to be equal to negative 3 or 3, depending on what R1 is. And now we have what R1, R2, R3, R4 is. And this tells us that, okay, now we want to find A, right? So A is going to be equal to the pairwise products, which is going to be equal to R1, R2 plus R1, R3 plus R1, R4 plus R2, R3 plus R2, R4 plus R3, R4. And then we can just plug in all the values that we have. It's going to be equal to, this is going to be equal to negative 9 plus, first we need to note that it doesn't really matter which value of 3 or negative 3 we choose for R1, because we can simply choose R2 to be the opposite value of it. And if we look at the sum over here, right, if we consider this here, we can note that R1 and, I can rewrite this expression so that it looks like this. R1, R2 plus R3, R4 plus R1, we can see over here, it's going to be R3 plus R4. We can just factor this. Plus R2, R3 plus R4. So we can see that it doesn't really matter what R3, actually, I can continue to simplify this. Since these are both R3 and R3 plus R4, this just becomes R1 plus R2 plus R1, R2 plus R3, R4 plus R1 plus R2, R3 plus R4. And note that R1 plus R2 is equal to 0 from what we have in the beginning, right? So this part just cancels out. And this just leaves us with R1, R2, which is going to be equal to, okay, I'm just going to write the values here. This is going to be negative 9, and this is going to be 5, which means this is equal to 4, or negative 4, sorry. And now if we go back to what A is, right, we can see that A is going to be negative 4, because it is going to be A over 1 is equal to negative 4, and we're not multiplying by negative 1 because A is the second symmetric sum. So A equals negative 4. And finally, C is going to be equal to, what is C going to be equal to? C is equal to just the products. We don't need to multiply by negative 1. So R1, R2, R3, R4, which is equal to negative 45. And thus we have solved the problem. We have that A equals AC. I guess this is like a notation that you can use, which is basically just means the pair of solutions AC is equal to negative 4, negative 45. Okay, now on to the next problem. All right, problem 3. This is going to be the last example problem that we do. So, suppose we have a polynomial x3 plus 9x squared minus 9x minus 8. And let's say it has roots r, s, t. These are just arbitrary variables for the roots. So now what we are asked to find is r plus s times r plus t times s plus t. Now there are two ways to solve this. One is more bashy, so more like just algebra, whereas the second one is shorter and more clever, and I'm going to go over both of them. So first, for like the longer solution, we can just multiply everything out. So this is just going to be equal to r squared plus rs plus rt plus st times s plus t, which is going to be equal to r squared s plus r squared t plus rs squared plus rst plus rst plus rt squared plus s squared t plus st squared. And then this is sort of like, so we have to first group this differently. So we can first notice here that there are two rst squares combined. So this is going to be equal to 2 rst. And then over here, we can factor the r. Wait, hang on, no. This is how we're going to do it. So we can consider this term here, right? So we have r squared s plus r squared t plus rst. So we can factor out the r. This is going to be equal to r times rs plus r times rt plus r times st, right? So you can notice that this is just going to be one of the roots times the second symmetric sum. And then, hang on. And then if we look at, let's say, no, let's use a different color here. So let's say we have the term with the s squared, right? We can see that there's also a term over here, and we have another rst. And this is just going to be equal to s times rs plus rt plus st. And then finally, what do we have? We have rt squared and st squared, right? And notice how there is no rst left, so we can't really create like another one of these second symmetric sums, right? But actually we can. So okay, so let me first write out the factorization. This is going to be equal to r times rs plus rt plus st. Okay, no. I'm just going to add it onto here. So this is just going to be equal to t times rt plus st, right? But also note that we can do this. We can add rst. But also but since this is not equal to the original expression, we can subtract the rst back later. And then using this, we can now turn this into, this is just going to be equal to t times rt plus st times rs. This is just going to be equal to t times the second symmetric sum. And since we have r times the second symmetric sum plus s times the second symmetric sum plus t times the second symmetric sum, we can factor this. This is just going to be equal to r plus s plus t times the second symmetric sum. And notice that we still have the RST over here. So this is what the factorization looks like. And what do we see? This is S1, this is S2, and this is S3. And if we look back at the polynomial we have here, we already have those values because we can find them from Vieta's formulas. So this is just going to be equal to, so what is S1? S1 is -9 times S2, which is equal to -9. And RST is going to be equal to 8. So minus RST means -8. So this is going to be equal to 81 minus 8, which is equal to 73. Yep, so that is the solution. And now there is a easier way to do this, or not necessarily easier, but there is definitely a faster way to do this. So suppose that Okay, so let us have some variable p which is equal to this value, r plus s, right? Now, what we can notice is that each of these terms is very close to the symmetric sum. It is very close to the first symmetric sum, right? In fact, what we can do is we can write this as is equal to S1, let's just call that the first symmetric sum, minus, we can notice that there's no t here, so this is going to be S1 minus t times S1 minus r times S1, not minus r, minus s times S1 minus r. Right? And this is going to be equal to, what is S1? S1 is negative 9. It's negative 9 minus t, negative 9 minus s, negative 9 minus r. Oh, and I'm going to add a coefficient of 1 here, just so that it makes it easier for us to visualize, right? So, let's say we have, okay, so let's say we have a function f of x which is equal to this, right? So then what do we notice here? This is very similar to the fundamental theorem of algebra, meaning that f of x is going to be equal to, since the leading coefficient of x cubed here is 1, we just have is going to be equal to x minus r, x minus s, x minus t, right? 1 times x minus r times x minus s times x minus t. And well, what do we notice here? We have that instead of x, we have negative 9. So the product that we're looking for is essentially just f of 9, right? Because it's just each of the x's is substituted with a negative 9, which is equal to negative 9 minus t, negative 9 minus s, negative 9 minus r. And what is f of 9, right? F of 9 is, we just substitute this into the original cubic that we have over here, which is going to be, not f of 9, f of negative 9. F of negative 9 is going to be negative 9 cubed plus nine times negative 9 squared minus 9 negative 9 minus 8. So we can notice that this is going to be equal to negative 9 cubed, and this is going to be equal to plus 9 cubed. And these cancel out, and we are left with plus 81 minus 8. 81 minus 8, which is equal to 73 again. And yeah, that is the second way to do it. It is, I would say, it might seem a little bit more like counterintuitive at first, like in the sense where you can't really immediately see how you can go from, the r plus s times r plus t plus s times s minus t. You can immediately go to this through the fundamental theorem of algebra. But I would say that sort of as you get more experience with doing these types of contests, it does become more intuitive in a way, and you'll eventually be able to sort of like see this kind of stuff immediately.